I am back with another quiz review video. So this is for quiz 2, protein structure, I believe. So let's get into it. Which of the following is true regarding the primary structure of a protein? So you had a few options. Now, those of you that got this right knew that the primary structure is maintained by covalent bonds. So primary structure, remember, is the sequence of amino acids. So some of the options were a primary structure is stabilized by hydrogen bonds. Nope, that's not true. It's the secondary, tertiary, and even quaternary structures, but more heavily the secondary structures that are stabilized by hydrogen bonds. Primary sequence is just the peptide bond itself, which is a covalent bond. Some of you responded that the primary structure is maintained by the hydrophobic effect. No. Primary structure is the sequence. So the way that the amino acids are linked together, the order in which they're linked together. And that has nothing to do with any kind of other interactions other than their direct sequence. Okay. Let's see, can I? Nope. Next question. In an alpha helix, the hydrogen bonds, what? So let's see if I can draw an alpha helix for you, kind of. Okay, so if you remember, you had some amino acids here in the alpha helix. Okay, now first off, the R groups are all pointed outward. I don't know if you remember that. They're all pointed out, sticking outward. So one of these answers is that there are no hydrogen bonds in an alpha helix. So the question is, in an alpha helix, the hydrogen bonds, and the answer is there are no hydrogen bonds. No, that's not true. There are. They occur between the amino acid side chains. Those are the R groups. No, that doesn't happen either. They are perpendicular to the axis of the helix. That means if the helix is going like this, then the hydrogen bonding is sticking out this way. No, that's not the case either. What is the case? Well, they're parallel to the axis of the helix. That means that the different residues, the different amino acids are actually hydrogen bonding to each other. And so this amino acid right here is hydrogen bonding to this one. This is the carbonyls and the amino groups, NHs, that are doing this. And so we get hydrogen bonding between backbone or, residues in this helix. If there's a one here. I didn't draw a good picture, but and so the hydrogen bonding is in the same direction as the axis of the helix. You might be thinking of beta sheets. Those have perpendicular hydrogen bonds. Next question. Which experimental technique provides an atomic resolution of every atom in a protein? You guys 100% got that right. X-ray crystallography. Mass spec gives you some masses of chunks of the molecule, definitely not in any kind of, picture of where everything goes. NMR, the same. It only gives you an idea of hydrogens that are near each other, but that doesn't tell you everything about every atom. An atomic force spectroscopy would be a scanning of the surface. Again, not going to show you everything inside of a protein. But crystallography manages that. And we get some nice computer models that we can look at. Next question. What type of secondary structure would a peptide composed only of lysine form? And the options are alpha helix alpha helix at less than 7, at 7, and an alpha helix at well above 7. I don't know if this is right. That little alligator, I can never do those. Little eats big, whatever. I don't know what that means. And then random coil at all pH values. Well, first off, we can look at this list of what amino acids. This is not the list. Sorry. can look at this list here and see what kind of secondary structure lysine would form. It looks like lysine on this list, 1.23 alpha helix. So it looks like it would be forming an alpha helix as opposed to a random coil. So that's our first option. Now, we need to rule out some of these pHs. So let's see. Now, the correct answer here is that the alpha helix would form from just lysines at a pH well above 7, as opposed to 7 or below 7. And the reason for that is going to be the side chain ionization. At a pH above 7, we're going to have less positive charges. If we are at a low pH, even a pH of 7, so for, again, I don't remember, I don't know what this is. I guess I should have just put pHs there, right? Dumb. Instead of these ats, that's why I'm all confused. So pH is above 7, pH is 7, pH is below 7. At both of these pHs here, lysine has a positive charge on it. They all have positive charges, but lysine specifically we looked at, NCCr is going to have plus, plus, minus, right? So at a low pH and at a high pH, this thing has an overall charge of +1. It's not until we get to a high enough pH, above 7, that we're actually going to lose one of those charges. Yeah, we lose that one. We're not going to lose this one until like a pH above like 10 or so, but we don't want to, because if we lose that one, then it's going to be negatively charged. But at the moment, above a pH of 8 or so, we lose that hydrogen, and this thing becomes neutral, 0, neutral. And so we're not going to get any repulsions. If every lysine was positively charged, we'd have a hard time sort of forming these good structures where they link up with each other. Also, they're not going to have their hydrogen bonding ability, right? Wait, is that the case? I know it has something to do with the pH. Yeah, it has to do with sorry, I was thinking of individual lysines all linked up in an alpha helix. No, they would be linked together. This guy would not be a free N, this would not be a free C. We wouldn't have to worry about these charges. We would, though, be worrying about the charges on this R group here. Okay. I'm going to have to come back and check on that one. I feel like I have to give you guys a better reason for why alpha helix at a high pH above 7. Sorry, I'm second guessing my reasoning on this answer. Okay, I'll give you a better answer on that when I do a little digging. Next question: what is the significance of the Leventhal paradox? I love your guys' answers on this one. I have to take Chem 150, yet I don't care about biochemistry. That is a paradox. Some of you put protein structure is related to protein function. Yeah, it is. But that's not a paradox, or at least that's not the Leventhal paradox. The protein must fold by randomly sampling conformations. That is also part of the Leventhal paradox, though that's not the point or the significance of it. So here's the Leventhal paradox sort of image, this little valley, this little energy valley. So for proteins to fold, they thought, these proteins will just kind of randomly flop around until they find their lowest energy states. Well, some proteins have so many atoms in them, so many different bonds and so many conformations, that just the time it would take for a protein to randomly check all the possible foldings would be longer than the time of the universe. So that can't be the way proteins fold. That was the paradox. So the information then for the folding must be encoded in the primary structure. As the amino acids are being put in, they're folding into their correct structures already, minimizing the number of, so as opposed to making a big long peptide and then letting it try to fold. These things fold as they're being made. Reduces the number of possibilities, makes these proteins fold much faster. That's the Leventhal paradox. So the information for the tertiary structure must be encoded, must be not like it has to be like I'm telling you it better be, but it must be like, hey, that must be how it happens. So it must be encoded in the primary sequence. All right. Next question. Which of the following best describes the function of hemoglobin and myoglobin? Most of you got this one right. The correct answer is that hemoglobin transports oxygen while myoglobin stores it. I think I've actually got an image of that in our protein function PowerPoint. Myoglobin transport oxygen, hemoglobin transports, myoglobin stores. And the reason for that has to do with their affinities. But let's see, what are the other options here? Some of you responded both hemoglobin and myoglobin store oxygen in the tissue. No, hemoglobin stays in the tissues. Oxygen travels around in the blood. They hand off to each other. Both can transport and store oxygen. No, not the case. Hemoglobin doesn't transport oxygen because it's not good at transporting oxygen. Transporting would be, you're good at transporting if you are able to take some oxygen from someone and then give it away to someone else. That makes you a good transporter. Storing it is you're someone who can grab some oxygen, but then you don't want to let it go. And so that's the difference in the affinities. Myoglobin has a much higher affinity. We can see that from this graph right here. Much higher affinity, which makes it good for storing in low oxygen conditions. And in those same conditions, hemoglobin doesn't really want to hold on to it that much. That makes it good at being a transporter because we can count on hemoglobin to actually give away the oxygen even though there's not much around. So that's the answer there. Hemoglobin transports, myoglobin stores it. Now, these next couple of questions are related. So how does one oxygen molecule binding to one hemoglobin monomer trigger the change in the affinity in the adjacent monomer? So we're looking at this image here, this image of the different squares turning into circles. So we're saying that one binding of oxygen in one of the tetramer portions of the hemoglobin actually affects the other. Now you guys had a few different answers here. Heme dissociates. Luckily, nobody picked that. An ion pair forms between histidine 146 and aspartate 94, or an ion pair breaks between histidine 146 and aspartate 94. So ion pair forms or an ion pair breaks, or there's no transition to a high affinity state. Somebody said that. So the question is, how does it change to a higher affinity state by binding? Well, the answer is not that there is no higher affinity state. There definitely is. Hemoglobin exists in two states, a low affinity state and a high affinity state. Now, we know that something about binding affects this. And so this is the image right here. You can see deoxyhemoglobin has its iron center attached to the histidine, and when oxygen binds, it actually lifts the iron, which pulls on the histidine residue, histidine ring here, and that histidine then breaks its bond with the aspartate 94. So it's the breaking of that bond being pulled away that actually confers the change onto the next subunit. So that's the step. All right. During vigorous exercise, ATP is hydrolyzed as follows, and it gives you the equation. What are the consequences for this structure function with the structure and function of hemoglobin? So we can take a look at that actually with any one of these graphs. So what we're talking about here is that when you're working out, you're burning energy, you're hydrolyzing ATP, and that releases hydrogen ions. Your pH drops. And so you can see right here in this table that as the pH drops, or at different pHs, the affinity for oxygen by hemoglobin actually is reduced. So hemoglobin at a regular, 40, the partial pressure of oxygen being 40 torr, or here, how do I want to say it? Yeah. So in the tissues, PO2 being 40, down here being 40, if your pH is 7.6, then your oxygen is about 90% saturated, if you follow the red curve. But in those same oxygen concentrations, if your pH is 7, then you're only about 50%, what am I? The hemoglobin is only about 50% saturated with oxygen. Um, so why is that a good thing? It's absolutely a good thing. If you were working out and you were burning more energy and you need more oxygen, you want your hemoglobin to be transporting more, to be letting it go more, to be releasing it more. You don't want your hemoglobin molecules being better at, or even just the same at their level of binding oxygen. You need more, so you want them to be releasing it more. Um, okay, so let's see. So there are a few things. So the hydrogen ions that are actually being released actually stabilize. So they stabilize the T form. So that's one thing that's kind of uh, well, there's a few actually that tie together. A few things that stabilize the T form. It's hydrogen ions. It's 2,3-BPG, which is the next question, and carbon dioxide. But specifically, lower pHs actually help the protonation of the histidine residue, right? The histidine. These protonations of the histidine residue actually stabilize the ion pairs between the monomers of the protein. So so yeah, so some of the other options for the answers were some of the things that you guys said was that if you reduce the pH, nothing happens to hemoglobin, only myoglobin. No, myoglobin isn't as affected by pH changes as hemoglobin is. Some of you said hemoglobin binds oxygen stronger as a result of the changing pH. That would make it harder for you to breathe as you were being more active. While it is true that you do need more breaths, right, and you do maybe feel like you're not getting as much breath, that's because your oxygen's going and doing a job. And yeah. And then some of you said the lower pH results in a deprotonation of the histidine 146, which stabilizes the ion pair. Remember that lower pHs mean that there's lots of hydrogen ions floating around. So that's going to have the effect of protonating something as opposed to deprotonating something. Okay, next question. During exercise and high levels of metabolism, the molecule 2,3-BPG is produced. What is the function of 2,3-BPG and in hemoglobin? And so, thankfully, none of you said it has no effect. Nobody said that it affects the pH in blood. Some of you said that it stabilizes the high affinity state, releasing more oxygen. That doesn't make sense. High affinity would be grabbing more oxygen, so it would make sense to say, carrying or transporting more oxygen, storing more oxygen. Those would all make sense with increasing the high affinity state. But it actually stabilizes the low affinity state, releasing more oxygen. It binds here in what we call the hole of the donut. And so that 2,3-BPG, you can see it here too. In the presence of 2,3-BPG at any given oxygen concentration, we're going to have lower saturation of those hemoglobin molecules. And again, that's a good thing. We want hemoglobin to have less affinity for the oxygen so that it lets more of it go in the tissues. All right, last question is, if you were to make a mutation to hemoglobin so that it can no longer form tetramers, what would you predict would happen? And the options were that it's impossible to predict. Nobody said that. That it would transport oxygen better. That it would bind oxygen with lower affinity than before, and that it would no longer be able to transport oxygen. Those were the options. So let's talk about which ones are right, which ones are wrong. So first off, it is possible to predict because we have a hemoglobin molecule that doesn't form any kind of tetramer, and that's called myoglobin. So if it can't form a tetramer, then it behaves like myoglobin does. And when we actually, add effectors that turn hemoglobin on, kind of make it more active, we see that it actually starts to look more like myoglobin in terms of its activity curve. But anyways, hemoglobin is cooperative because of its tetramers, but that cooperation doesn't always mean that it's better at something. I mean, it does. So let me clarify. The cooperation of hemoglobin does not make it bind oxygen better. It actually makes it bind oxygen worse. But that's not the point. hemoglobin is a transport molecule. And so the cooperation of hemoglobin actually makes it a better transport molecule. So it makes it better at transporting by making it worse at binding. So if it were no longer able to form tetramers, it would be actually, oh wait, I'm sorry. Yeah. Sorry, yeah. That's what I just said is true because I'm talking about the cooperativity. It makes it worse at binding so that it can transport better. So if you remove the ability to bind, then you make it better. Remove the ability to form tetramers and to cooperate with each other, then you actually increase the affinity for oxygen. It becomes more like myoglobin. And a molecule that has higher affinity for oxygen would not be a better transporter. It would be a worse transporter. It would be a better storage molecule, but it wouldn't be a better transporter. And so that's why it would transport oxygen better is not the right answer. And also it would bind oxygen with lower affinity than before. That's also not the case. It would bind stronger than before. All right, guys, that is quiz 2. I think you're going to take quiz 3 tomorrow, right? Or are you taking it today? No. Quiz 3 comes tomorrow, Thursday. So I should be either Thursday or Friday posting a video for that. And then you got your first exam coming. And I'm hoping to try to do a Zoom session between 12 and 1 tomorrow to answer any questions that you guys have. All right. See you guys next time.